Hi everybody, I'm Thomas Kalaga and I'm the team lead of the Hydraulic Smart Glove team, 22003. I'd like to introduce my team as Brandon Bowie, Cole Bauer, Connor Pierce, and Corey Saunders. I'd also like to make a special mention to our sponsor, Paul Efron, who has been super supportive of our design processes throughout the year, and I'd also like to give a special shout out to Bob Messenger, our mentor, who has provided me and my team with invaluable insight and holistic support for the whole semester.
The Hydraulic Smart Glove provides an interface for measuring the forces in everyday physical activities. Real-time data allows users to track the instantaneous forces as well as the total time under tension. With the Hydraulic Smart Glove, fitness fanatics, construction workers, and physical therapists alike can work safer and smarter. The design utilizes a hydraulic tubing system comprised of tubing, hydraulic fluid, and a manifold that is connected to a pressure transducer. This allows us to measure the pressure applied to the tubing. The team developed software that approximates the weight being lifted and the work being performed based on the pressure inside the tubing. Sensor data is collected by an Arduino Nano development board, which is displayed using a graphical user interface on an LCD display. The user will be able to interact with the GUI via buttons to calibrate the system, change units, alter brightness, and reset the time under tension.
So we've shown how our system works, but now we need to find the relationship between the weight that's applied to the tubing and the electrical signal produced by the pressure sensor. We grabbed a series of dumbbells and plotted the bit values returned by the sensor at each weight, so we would put a 5-pound weight on the tubing and see the value that was returned. Every time that we turn on the glove, the pressure transducer is recording the bit values with no weight applied. We save this as P0. As we apply weight, the pressure inside the tubing changes, and as such, the bit value increases, and that change is proportional to the change in pressure. The resulting curve shows our calibration equation. You can recalibrate the glove by pressing calibrate, which updates P0 to whatever the current ambient pressure is. Let's go over a couple quick examples of how hydraulics work in action. The first guiding principle behind our hydraulic design is the fact that liquids are incompressible. When we sink this plunger, it displaces 1 foot of water, and on the other side, the water level rises by 1 foot. In this arrangement, sinking the plunger raises the water level in 3 other tubes. This water raises by the same amount in each tube because the force is distributed evenly. If we displace 12 inches of water, 4 inches of water will be displaced in each of the 3 tubes. We see this concept every day when we press on our brake pedals in our cars, and the force is distributed evenly to all 4 tires. When we're driving in the car and we need to stop, we push down on the brake pedal, and that distributes a load to all 4 of our brake calipers at the same time, slowing down the car. Our hydraulic smart glove works on the same principle but in reverse. When we apply a weight to the glove, it compresses the tubing, and the fluid inside of the tubing is incompressible, so that change in pressure is registered at this pressure transducer. We can mount a screen to this box here and display the weight so that you know exactly how much weight you're carrying.
Time under tension is one of our specific sponsor requirements. We collaborated with Paul when outlining the rest of the system requirements, which we will go through here. Some requirements of note include 2.2, which ensures that our product will be safe to use because our electrical components will be blocked off from the user. Also requirement 4.3, which sets a battery life expectation for the glove. We set this in accordance with the scenarios we expect the glove to be used in, such as in a warehouse.
And on this last slide, we can see the time under tension requirements, that being total time under tension, the trip time under tension, and the ability to reset your time under tension.
Within the hydraulic smart glove, we have 3 major subsystems, which are labeled as power, electrical, and hydraulics. The power subsystem consists of a 3.7 volt battery and a power booster, which boosts the voltage to 5.2 in order to power the Arduino, and the pressure transducer. The electrical subsystem houses the Nano, the display, and the buttons that are used to interact with the graphical user interface. And lastly, the hydraulics subsystem consists of a manifold, fittings, ferrules, and tubing in order to simulate the fingers of a hand and connects to a pressure transducer. The transducer can handle up to 150 psi and has a maximum error within 0.5%. The power subsystem provides 5.2 volts to both the microcontroller and the pressure sensor separately. The pressure transducer outputs an analog signal, which is a voltage between 0.5 to 4.5 volts, which is then sent to the Arduino, calibrated, and then displayed on the GUI.
Okay, now on to the future considerations. For future designs, implementing a PCB would be advantageous because it would make the GUI more compact and it would allow it to fit better to the rest of the glove. We would also recommend introducing flex sensors to the tubes so that errors would be reduced in the pressure readings associated with flexing those tubes, as would happen with bending the fingers. Another consideration is how to integrate the tubes to the fingers of the glove. For this prototype, we used Velcro to attach the tubes to the fingers. A better method may be to actually sew the tubes onto the fingers.
To conclude our Design Day video, we'd like to recap some of the key things about our project while taking you through our Design Day poster. Simply put, our glove aims to be able to measure how much time you are exerting force on an object, and to correctly display the value of a given weight. A glove like this has lots of practical applications. It can be an informative tool for warehouse employees who can finish a day having insight on how long they've lifted. Our hydraulic smart glove design consists of 3 subassemblies: hydraulic, electronic, and sensor. These subassemblies are integrated together, and on the LCD display, you can see the GUI that we've created here, allowing you to run, calibrate, change the brightness of the display, switch the units, reset your time under tension, and even put the display to sleep. The GUI display on the right is actually showing you what the run mode looks like. You can see the raw values coming out of the transducer, the uncalibrated values, calibrated values, and the time under tension. Our resulting design satisfies a number of requirements given by our sponsor. Our team has constantly been trying to improve upon our design, and what we've delivered here on Design Day is a usable, wearable prototype for a hand of any size.